shortly here. So, perfect. That exactly as I requested. Not too much marketing. This is very clean, and it's focused on 5G. Excellent. So I'm pleased to introduce our final speaker before the panel discussion. Is Ian Wong, and Ian has the distinction of actually being a WNCG alumnus, and so he was sitting here many years ago now. Okay, he says 13 years ago. I think it was like 16. Wait, no, I wasn't here 16 years ago. But he was here, a number of years ago in that first group of students that was a part of the WNCG, and it's really exciting to see our graduates that have achieved so much, and then now they're coming back to talk about what they've been learning. So I think this is a really exciting opportunity for us. So Dr. Wong, will you come up here and kick it off? Join me in welcoming Ian Wong.
Thanks for the kind introduction, Robert. And it's really an honor for me to come back here. I remember being part of the poster session 13 years ago at this exact Texas Wireless Summit. And special thanks to Ted, of course, for starting the center. And Robert and Jeff and Gustavo and Sriram, you were all I took classes from all of you. And frankly, I wouldn't be here without you guys. So I'm really proud and honored to be here. All right, so not too much marketing, but I start with, my company, of course. So they're the ones, in fact, paying for my salary. So I'm from NI, and I was asked by Jeff and Robert to talk a little bit about waveforms. So I wanted to title it a bit more like how Robert did his panel, was that 5 years ago when he said, "Is the phi layer research dead?" So hopefully I won't be as wrong as he is. Yeah, exactly, right. So now that RCR Wireless is here, this is another tagline you could use potentially. Anyway, so I do want to start off with, it's kind of the last talk of the day. I want to, all of you are the wireless experts here, right? Who among you think that OFDM is dead? A whopping one. Let me give you some inspiration. How about some creative visualization? Okay. So only Gerhard thinks that OFDM is dead. Well, hopefully, Robert and Gerhard, the people that matter, think that it's dead, which is great. I'm kidding. No, all of you matter. Come on. But I mean, the purpose of this talk is not to convince you that OFDM is dead or not, but I wanted to show you the strengths and weaknesses of OFDM, which is obviously the dominant modulation scheme of all of the standards you heard about today, Wi-Fi, LTE, even DSL and optical. I mean, all of these guys are using these technologies, and hopefully, but then let's suppose that Gerhard and Robert are correct, and let's do some visualization, right? Suppose it's 2020, and we're doing a eulogy for Mr. OFDM. What would it say? First of all, we all know it was born in 1971, the brainchild of, Weinstein and Ebert. Very brilliant idea. Use a DFT to kind of orthogonalize a broadband channel. And I was looking for a picture that denotes OFDM a little bit so you can visualize. The best way I found is this, right? Like if you see this, you kind of know this is the OFDM spectrum. How many of you? How many of you have heard of the term Barts Head? Barts Head? Come on, more of you, right? Like maybe about half. All right, so if there's anything you learn from this talk, at least, is you at least now know that that's called Barts Head. So there you go. So just creative visualization there. Like it's because of that OFDM spectrum. But let's talk about what are the strengths and weaknesses of OFDM. First of all, I think the biggest strength is its simplicity, right? It's FFT based, which is very efficient. And at the end of the day, it's a single tap equalization for a frequency selective channel. That is really awesome. Number two, it's actually fast. So Gerhard talked a little bit about the support of MIMO. A lot of the other schemes don't support MIMO. OFDM naturally supports MIMO. And in fact, OFDM, in a way, was almost designed with MIMO in mind. Like you can think of it as every of these sub-channels, you can process the MIMO and remove the interference of the different antennas on a per sub-channel basis, which is really great, kind of going back to the simple. And then it's also very resilient. right? Like we all know this. I mean, it's robust to multipath fading and time synchronization errors because of cyclic prefix. So these are all great strengths of OFDM. But then, as with any great strength, there's also a lot of weaknesses. So one of the biggest, I think, weaknesses is the fact that it's power hungry. I mean, it needs, it has a high peak to average power ratio, as you all know. And we kind of need these, either linear or linearize these power amplifiers. I mean, we've devised new methods, DPD, envelope tracking, and all that to make it a lot better. But at the end of the day, this could be the number one downfall for this modulation scheme. And it's also noisy. This is one thing that's important for a lot of the 5G use cases, which we will see, is it's got very large side lobes, as you see. And in fact, it's got low spectrum agility. So what do I mean? So with the FFT, you got basically about just at most of 30 dB attenuation on the side lobes, and you really need at least 60 or 70 or more of that if you want to kind of intersperse, let's say you have machine type communications, Internet of Things, the traffic within, let's say overlapped on top of 4G LTE. You kind of need those side lobes to be really low to be able to interwork graciously, let's say, with legacy systems. And finally, it's also very sensitive, right? Carrier frequency offset is one of the biggest kind of hurdles. And however, I think the biggest downfall, if it were to fall, is the uplink interference. Like with OFDMA, you kind of need all of the signals coming up to the base station all lined up. Although you have the cyclic prefix to help there, it can't be too big for efficiency purposes. So at the end of the day, if density is one of your most important things for 5G, like for the Internet of Things, this is pretty problematic. So we will not be able to support asynchronous ways of being able to connect to the network by millions, if not billions of devices. But despite all of that, we all know that this great modulation scheme has impacted almost every single modern communication scheme that we all know of. Billions of devices, according to Broadcom, trillions of dollars of economic impact, if you kind of count all of the devices, equipment, carriers around the world. And maybe to end the eulogy in 2020, we kind of talk a little bit about its descendants, right? Its offspring. So it's going to be survived by a single carrier, which is interesting because you would think that we're in fact probably going to go back to single carrier, or a lot of the different, I think Farouk called it gimmicks of the different modulation schemes. But hopefully it's not just gimmicks. So there's actually good signal processing foundations for actually using these new waveforms. So for the rest of this talk, I'm going to first motivate a little bit on kind of why. I mean, we talked a little bit about why we need 5G, like this is kind of fresh news, I guess, for a lot of you guys who don't follow the standards or not too much. It was just last month when 3GPP actually got together for a 5G workshop. So apparently someone is very distraught that OFDM may be on its way down. But in any case, there were 550 delegates from all over the world representing all the companies here that you've heard of. Were represented. 70 presentations back to back, including NI, we also presented here, showed our views there. But at the end of the day, this is the consensus. This was actually taken from the chairman's summary of this meeting. So if he were to summarize what this meeting came out, of the 3GPP is, first of all, they want to have a new radio access technology. I mean, maybe that's obvious, but 5G will be new, and it has to be supporting, a variety of new services. At the end of the day, like from a carrier's perspective, if you think about it, like AT&T, Verizon, they're basically, at the end of the day, our customers. Right? We're all, they're our customer, and then their customers are, of course, the broad public, and they see a need to be able to grow their service offerings to beyond the smartphone, beyond the user-centric communications to more machine-type communications, industrial communications, and so on. And to me, the most important thing that was kind of a consensus from the whole body is they wanted to call it should be designed for forward compatibility. So what does that mean? It's a euphemism for not backward compatible. That means we don't need to make sure that 5G, right, is backwards compatible to LTE. I mean, if you think about it, every big generation, every big leap, from GSM to CDMA to LTE, the modulations are totally different and thrown upside down, and it's okay to do that for 5G, and that's the consensus of the whole body. So you could take a lot from that. And finally, the three main use cases that were heavily discussed and that were also agreed upon as the main use cases to be studied for 5G. There's some disagreement on which is the priority of which to look at first, but there's really three main use cases. Okay, if there's three things that you take away from this talk, this is the second one, apart from Barts Head, there are three main use cases. It's enhanced mobile broadband, massive machine type communications, or basically massive IoT, and the third one is the ultra reliable and low latency, which is what you heard a lot of the use cases Gerhard talked about this morning. So these are the three things. So this is a diagram taken from the ITU recommendation. It's almost like the white paper or the recommendation of ITU to consider what 5G is. And it was pretty much, I would say, 80% of the delegates used this diagram to show kind of the three main use cases. On the top end, enhanced mobile broadband, right? That is the user-centric, give me more data, give me 3D video, give me Ultra HD on my phone or my laptop use case, right? And then you go down on, let's say, the right edge here is, although the throughputs kind of go lower, there becomes more and more kind of requirements on latency to be lower, reliability to be higher. That's when the use cases of being able to support industrial automation, for example, and mission-critical applications, and of course, self-driving cars, which was talked about a lot today as well. And then on the other edge is when you kind of go down, throughput again can go down, and then you kind of talk to machines a lot more. Smart homes and smart buildings needs a bit more throughput. But then once you go down here, it's the massive, smart city, sensors in every lamppost, sensors in your garbage can on the street, and so on. So that's kind of where we really need the network to be, if you think about it, redesigned from the ground up to be able to support these types of systems. And I mean, from a 3GPP standpoint, this is important because you may have heard of some startups that are now providing networks purely for IoT, like LoRa is an example. Sigfox is another example. These are two kind of up-and-coming, brand new networks from the ground up just for IoT, which is kind of really threatening, in a way, 3GPP a little bit, or kind of our carriers. And if you remember, about a decade ago, 2004, it was WiMAX was one of the impetus for LTE to be born. So you kind of think about it, it's like there's a sense of urgency here that we do need to figure this out. So what are the requirements here for these three? The first time I saw this diagram, I mean, it's not a typical diagram us engineers look at, but apparently this is called a spider diagram. But basically the tentacles of this shows kind of the different, metrics or performance metrics that 5G needs to support. So let's start with the more kind of marketing peak rate, right? It's like 20 gigabits per second, right? And 100 megabits per second everywhere, 1 gigabit per second hotspots is what, this is obviously a big jump, order of magnitude jump from what LTE Advanced can do today. And talking a little bit about mobility, we want to be able to go up to 500 kilometers per hour for the high-speed trains use cases. And basically, this kind of high, medium, low shows you like for enhanced mobile broadband, for example, these are the key performance indicators that better be met for it to be a viable, viable network for enhanced mobile broadband. Excuse me. And for IoT, for example, obviously it's the connection density that's the key performance metric, and they want to be able to get 1 million devices per square kilometer. And then, of course, for ultra-reliable, low latency, it's the latency and also mobility. If you want to try to kind of talk to a self-driving car, you kind of get to the level of mobility compared to a flower pot or a trash can that you don't need that. So this is an interesting diagram to kind of frame the conversation on how we really need to redesign this network and make sure that we kind of attack these use cases kind of head-on, because obviously we can't do everything at the same time. So kind of looking at this and kind of going back to the question of is OFDMA still suitable, I kind of rearranged the strengths and weaknesses here and wanted to group there's obviously there's a lot of strengths and weaknesses that are shared, but at the end of the day, for enhanced mobile broadband, I really see the ability to really, of course, retain and really improve upon the fast, right? It needs to support MIMO. It needs to be wide bandwidth, right? And even wider bandwidth, like 100 megahertz was kind of, in a way, the minimum bandwidth that was already talked about for 5G, instead of 20 megahertz. And it needs to kind of go, really the two things it needs to overcome are its kind of sensitivity to CFO and uplink multiple access and its power hungriness. For massive MTC or massive IoT, there's a lot of issues, frankly. And we need to make sure that it's still simple and even make it simpler. Then it also needs to solve the large side lobes problem and the power hungry problem. And for ultra reliable low latency, it's a bit, definitely the harder problem, and Gerhard talked about it a lot in his talk, but we definitely need to solve sensitivity and the large side lobes as well for that to be really reliable. So just very quickly, I want to talk through an overview of each of these techniques that are now being talked about and proposed for enhanced mobile broadband as a start, right? So first of all, the biggest issue, at least in my mind, is the power hungriness, especially if you go to millimeter wave. I've got 4 minutes, yes. So let's talk about single carrier techniques that are being proposed. And also for spectral efficiency, one thing that's being proposed by NTT Docomo is a technique called non-orthogonal multiple access. I'm going to give a kind of quick slide on that. So very quickly, it's kind of silly to talk about SCFDMA as part of 5G waveforms, but at the end of the day, this is the first modulation scheme that's widely adopted that's not OFDMA. So already just for LTE and LTE Advanced, we need to solve that power hungry problem. This is obviously, it's a lot of you probably know this, but it's a DFT spread OFDM at the end of the day. It's already adopted by LTE and LTE Advanced. And the best, really, at the end of the day, it's all about lowering, or saving power on the mobiles. And that's, if you look at this chart right here, it is staggering the difference between OFDMA for different modulation schemes and what we can achieve with SCFDMA. This is kind of the amount of power back off, this is the cubic metric of the modulation scheme. So like that being said, I think SCFDMA is still a kind of very viable technology for the uplink, and we should probably seriously think about, like, not everything needs to be potentially be thrown out. The next thing is millimeter wave. So we heard a lot about that today, and I don't want to steal the thunder too much from Amitabha, but we work together very closely with Nokia. But this is basically their proposal here is to go back to single carrier, but then kind of have the advantages of lower PAPR, but still reap the benefits of easy equalization by doing block-based, frequency domain equalization on the receiver side. So it's lower PAPR. You can do TDMA with beam steering because you have smaller cell sizes, small slot lengths, few users. And our friend here, Amitabha, actually showed this live in our keynote stage just about 2 months ago of a 70 gigahertz, 10 gigabit per second. So I'll definitely let Amitabha talk more about that later. Another interesting, I would say, proposal in 3GPP today is a concept called Norma, or non-orthogonal multiple access. And this is really trying to push more on top of existing, it's compatible with existing concepts like, it could still use OFDMA, it could use new waveforms, it could still use MIMO, but then they can actually superimpose users on top of each other on a per sub-channel basis by kind of exploiting, really, it's trying to exploit the path loss difference between users. Like typically a big cell would have users close, users far. Norma basically kind of shows that. At the end of the day, you just kind of push the complexity to the receiver and do some successive interference cancellation. This is nothing more than commercializing superposition coding. If you kind of like, for you information theory guys, this is actually what's being talked about today. And there's also a test bed being done by NTT Docomo on this scheme. And then, just quickly for my remaining time, let's talk about the alternative multi-carrier techniques that are being proposed today for solving really both the MTC and the ultra-reliable low latency. And I want to talk about, there's actually a lot more than these three, but these are the three that I hear a lot about, always being talked about. So just very quickly, an overview of this. The first one is filter bank multi-carrier. I mean, this idea actually predates OFDM. So OFDM, before the DFT was used, was thought of as really a filter bank multi-carrier technology. All this is doing is kind of really exploiting the fact that we can use polyphase filter banks for pulse shaping. So now you can actually knock down side lobes a lot better. It has better spectrum agility. You can have much lower ICI. The most talked about FBMC scheme is an O-QAM, offset QAM modulation, wherein it's actually not orthogonal in complex plane, but it's orthogonal in the, so it separates out the real and imaginary parts and staggers it in kind of the different tones in your spectrum. The biggest challenges, MIMO is not straightforward because of the non-orthogonality in the complex plane, and also, of course, receiver complexity. And again, there's a lot of companies that are pushing for this, and they've also shown some test beds as well. This is from a demo in Globecom that was shown by CEA lady. The other one that's also being talked about a lot, and Alcatel-Lucent is one of the bigger proponents of this, is UFMC, Universal Filter Multicarrier. This is kind of an idea in between the extremes of just filtering basic OFDM to doing a full filter bank on a per subcarrier basis. So the idea here is very simple. Just do your filtering, on a per resource block basis. A resource block is kind of this unit of time and frequency in LTE. Just do it on a per resource block basis. That way you can do it on a per user basis, and you can achieve the benefits of the lower side lobes, the better ICI kind of robustness, but without the complexity of per subcarrier filtering, but also being able to support MIMO. And there's been some kind of research out there that shows that this actually performs a lot better in a comp scenario, kind of the coordinated multi-point distributed MIMO scenario. This shines way better than OFDM. And then finally, Gerhard already had a full talk this morning. I'm not going to go into details, but GFTM is a great alternative as well. And at the end of the day, it supports MIMO. It's great for different block lengths and 2D structure. So it allows you to support all the different use cases that MTC needs, all the way from really, really low latency for tactile internet, kind of trading off latency versus reliability and throughput very gracefully. So in the end, I wanted to kind of, a lot of us, we're used to writing papers, a lot of the academics here, a good kind of subjective comparison here. I don't want to talk about it too much, but at the end of the day, there's pros and cons. The jury is still out there. And I talked a little bit about waveforms for millimeter wave. This table I actually copied from a paper on talking about waveform design for massive MIMO. Right? There's actually opportunities to have smarter waveforms also for the concept of massive MIMO. And Robert here is about to kick me out. So I will end with my only marketing slide. Really, I'm marketing for the National Science Foundation here. It's like, this is from them. It's like, at the end of the day, we have all these schemes. They're great ideas. But in order for breakthrough research to happen, I think you really need to build it. Right? We talked about a test bed from Broadcom and LA, a test bed from Qualcomm. And we want to see more of this, test bed from Nokia, test bed from Samsung. That's kind of where we can objectively test out ideas in a fair manner. And that's at least my spiel here. And just so that, I want to see whether I was able to change any minds after my presentation. So poll again, who thinks OFDM is dead in 10 years? Yeah. Yes! I was able to turn 3 more. Thank you. All right. Before I end, I do want to always quote my CEO. It's always good for your career. And let's watch 10 years later on what will happen. All right, thank you.
Pullback is only 4 dB, like as a worst case scenario relative to like some reference. That's not very much. I mean, compared to like what Farouk was talking about today in terms of energy efficiency, that's 1 factor of 2, basically. Why is this such a problem?
I mean, for a handset, really every millijoule counts, right? If you're talking about Samsung versus Apple smartphones, they're fighting against the last minute of their smartphone being on. So I think it really matters that, and it actually matters more for MTC, right? We're talking about devices need to turn on and stay on for 10 years and not be serviceable. So I think we need every millijoule, and we have to be smart about designing those waveforms for that. That's my opinion.
All right.
Okay, so now we're moving into the second to last phase of the tech